Yes, Richard, can you hear me?
I can hear you. I'm
Oh,
sure
good.
everybody else can too.
Okay.
Uh, Bruce is engineer and compliance and enforcement manager, which sounds ominous, with the Placer County Air Pollution Control District. Prior to that, Bruce was with the Energy and Environmental Research Corporation as an air pollution control consultant to the waste and power industry. Uh, Bruce, we'll turn it over to you now, and it's all yours. Thank you.
Okay, thanks, Richard. I wanted to today go over two pretty simple procedures that we've developed and produced in writing that value the greenhouse gas benefits of producing energy or biochar from forest waste materials. I'll also touch on the benefits produced from reducing black carbon, and then also talk real briefly about some complicated work we're doing trying to extend the benefits of fuels treatments that Tadashi had talked about a couple weeks back, and also discuss briefly some examples, some real-life examples of biomass projects that we've supported. So, as Richard and Tad talked about in some detail, forest management projects produce both merchantable material and also waste material byproducts. Now that merchantable material that gets to the lumber mill and turned into wood products, those greenhouse gas benefits are clearly defined in and how you value them in existing protocols through ACR, CAR, ARB cap and trade forest programs, and also similar to what Bill Stewart described a couple weeks back. What is not put down yet is valuing the energy or the or potentially biochar from the byproducts. And most obviously, fuel reduction projects produce biomass, waste biomass. But as Richard mentioned, reforestation, improved forest management, even urban forestry, forest pest control projects will also be producing waste materials that could be tops, limbs, brush, stumps, just the excess material from that forest management project. So all greenhouse gas evaluations need to start with a baseline, or if you didn't do the greenhouse gas project, what would the emissions be? So we start with the material is produced, and now we have two options, or we have a bunch of options, but we're looking at two scenarios. And the baseline scenario is I take that material, and as Tad mentioned, very frequently, commonly, as air districts know, because of the condition of the Sierras and because of a lot of the reason of the work, that material is pile burned. Alternatively, it can be chipped or just laid on the field, or it could even go to landfills. So those are three options that set up the emissions from the baseline. And then alternatively, we have an energy demand that we produce through fossil fuels, other types of renewables, but there's a carbon intensity of producing energy. So that's the baseline. And then alternatively, we have the biomass project, and that involves collecting the biomass waste at the landing sites, processing it, chipping it, grinding it into a chip van, transporting that material to the energy facility or the facility that produces biochar, and then characterizing those emissions from those two scenarios. And so we've developed with Tad's firm's help over many years ago, we developed a written procedure which accounts for the benefits from those two scenarios. And we've codified that procedure called the Biomass Waste for Energy Greenhouse Gas Offset Project Accounting Protocol. Recently, we've got it approved and adopted into the California Air Pollution Control Officers Association, or CAPCOA, we've started 6 of the air districts have begun a greenhouse gas exchange registry where we're sponsoring projects that reduce greenhouse gases under approved protocols, and then using and trading those credits for mitigation under CEQA, or California Environmental Quality Act, requirements. So these two, there's the benefits from this project come from reduced methane from the open pile burn or the disposal into the landfill or the field, and also displacing the fossil fuels. And these protocols can be found on our website as well as on the CAPCOA Greenhouse Gas Exchange website. So the protocol sets up, again, these two scenarios, conditions where the baseline has CO2 and methane emissions from either the open burn, decay, and the energy supply from the conventional sources. And then alternatively, we characterize the greenhouse gas emissions from the biomass project, which would be the diesel or gasoline needed to run the engines for the chipper and the transporting, and then the actual energy facility has emissions as well. And so and then we add those up on each side and subtract them, and then that's the benefit of the program, of the biomass activity. So just going quickly over the procedures that we need to collect during a project, we of course need accurate accounting for, again, the amount of fuel that's used in the grinders, in the chip vans, or water trucks, or bulldozers, or any other equipment that's needed to run the biomass project. Then we characterize the energy that came from the facility itself, getting, as Tad mentioned, bone-dry tons, wet green tons of material, energy content of the material, moisture content, emissions factors of the facility. And then a critical component is what's referred to as the heat rate of the biomass facility, and that's the valuable energy or electricity that you get from the process versus how much energy or biomass you put into the unit. And that could produce electricity. It could be cogen electricity, on-site steam, or it could alternatively be use of biomass to produce heat on-site that might displace natural gas. Okay, so then on the baseline side, which actually didn't happen, but we need to make some estimations for that. So if it was a pile burn, we have to estimate how much material burned in the pile. We have some assumptions, some recommendations in the protocol for that. We have recommendations for methane and CO2 that comes off the pile burn. There's established procedures for landfill decomposition of the organic material in the landfill and how much methane that produces. So the protocol establishes those, and then finally it also goes through and a critical piece of this is determining this biomass electricity avoids or displaces a certain amount of the current grid, and we recommend that you assume conservatively a natural gas combined cycle greenhouse gas emissions, which is a very efficient process. Alternatively, you could use the local regional supply if that's more appropriate, or you could use what is referred to as a marginal supply of electricity, which might be a single cycle gas turbine. And then if you're producing heat, you would be displacing natural gas or electricity. Cogen, you would be displacing both electricity and heat. Okay, so we've conducted over the last 5 or plus years a number of demonstration projects. The district has supported and sponsored some real life case studies where we've actually made these measurements of all of those parameters I just described for a biomass project. Of course, you have to again assume assumptions for the baseline. One is shown here where we move material from above Forest Hill, Forest Service land. They had about 5,000 bone dry ton of material that was going to be pile burned. We made up the difference in cost to get it, to truck it down to the nearest energy facility, a Sierra Pacific Industry facility in Lincoln, at their lumber mill in Lincoln, about 60-mile one-way trip. We chipped it, trucked it, made electricity out of it. We did a similar project at the UC, more recently at the UC Berkeley Blodgett Research Center above Georgetown toward Tahoe. Moved that to the Buena Vista biomass plant. I think that might have been 70 miles away, and carefully characterized the diesel fuels of the chippers and trucks. And then this slide is not showing up too well. I have a spreadsheet that I've developed that I'll share if people are interested, where you can put in all these parameters to calculate the CO2 emissions from your project or your estimated project. So it's not too readable for some reason. And then I will, this one's not showing up too well either. This is the results of a project. The right side is the greenhouse gas emissions results from the first project I mentioned, the SSO project, where the dark green bar is the right side is the baseline. The dark green bar, oh no, I apologize. The right side is the biomass project. The dark green is the CO2 from the biomass facility. What you can't see, the very small light green bars on top of that are the trucks, and the diesel fuel from the chipping and trucking, which tends to be a very small percentage, actually, even for a fairly long transport distance, which is a byproduct of the very large energy quantity in a 25-ton chip van versus the relatively small amount of gallons of fuel you need to chip it and truck that material. And then the left side is the baseline. The light green is the emissions from the open CO2 from the open pile burn. The green stripe is the methane from the pile burn, and the blue stripe, which is the benefit, is the avoided natural gas combined cycle from the amount of electricity that the bioenergy project produced. And again, I apologize for this slide. It looks better. I don't know why it's turning out like this, but there's greenhouse gas benefits, as I just described, for most projects, but the criteria air pollutant benefits are huge. Criteria air pollutants are traditional air pollutants of fine particulate matter, nitrogen oxides, carbon monoxide, and volatile organic compounds. Those are contributors to ground level smog, ozone, fine particulate haze. So these are our traditional air pollutants. And the air districts are very excited and encouraged by biomass energy projects because they produce, as you can see, incredibly lower significant reductions of all of these air pollutants compared with pile burning. The orange bar, dark orange bars are the pile burns. The guys next to them in green are the bioenergy projects. So again, as you can see, there's huge reductions, huge benefits. I seem to be missing a slide here. I apologize. I've got some resources for papers on these studies that, or maybe that's talked about later, okay, that I'll point to, or you can email me and I'll provide to you. So the other, a more recent acknowledgement, a benefit of biomass energy projects compared to pile burning is this black carbon. Black carbon comes from three sources, primarily diesel fuel combustion, coal combustion, and biomass burning. And diesel is very well controlled in California at this point for the most part. Coal-fired power plants are non-existent essentially in California. So the big source of black carbon in California is biomass burning. That could be in your fireplace, that could be in pile burns, it could be in wildfires or even prescribed burns. Black carbon is a very potent greenhouse gas. It's referred to as a short-lived climate forcer pollutant. It's in comparison, if CO2 is 1, methane is 24, black carbon for that same amount is 900. So very, very concerning for climate change. And this soon we're going to be, this shows the comparison of black carbon from a pile burn versus black carbon from trucking, chipping, in the energy facility. So kind of comparable to fine particulate, you get huge, huge benefits to an energy project that will produce big climate benefits as well. So this hasn't been incorporated, black carbon hasn't been tied up into our official written procedure yet. We're sponsoring some research to quantify, characterize very accurately what the black carbon emissions are from all different types of pile burns. We'll be looking at different pile type materials, stacking types, moisture levels, and then hopefully we'll develop a lookup table or some kind of conservative procedure that one can use to value the black carbon or reduce black carbon emissions from going toward an energy facility as opposed to a pile burn. Okay, here we've got a peer-reviewed published paper of that first project at that link, at the first link. The second link is the upcoming peer-reviewed report for the UC Berkeley Blodgett project, and that will be shortly. It'll be shortly published in the California Agricultural Journal, but you can find a preliminary copy at that second link. Okay, so moving on to biochar. Biochar as Tad described in some detail, is a byproduct or an intentional product of taking the woody biomass and gasifying it or pyrolyzing it. And so you end up with this very rich, carbon-rich material that's very stable and very doesn't degrade or decompose. The structure of the biochar is such that the carbon is just locked into that material for a long, long time. That biochar has value for sequestering carbon potentially. It also has value for reducing or improving water retention. It's applied to agricultural crops, field crops or orchard crops, and provides research is coming out that's really showing tremendous benefits to the water retention of the field and the nutrient. It serves as a fertilizing value. The crop growth is improving. That work is coming out. And then usually it's associated with both a renewable energy aspect and a biochar from the gasifier. So we've contracted with, over the last year, half a year, we've contracted with the Persino Group, the International Biochar Initiative, and the Climate Trust to develop, they in a parallel effort, were developing a biochar greenhouse gas offset protocol that they were working through the American Carbon Registry. So we contracted with them to develop a similar, to build off that protocol and get it set up into our CAPCOA greenhouse gas exchange. And that we've completed a draft protocol. The protocol's gone through a stakeholder review, a public review. We've responded to some comments. It's being evaluated for approval as we speak. You can find a draft version of the protocol at that link. The key piece of the biochar greenhouse gas protocol is assuring that biochar that you produced really is stable and doesn't degrade. And the primary factor that's used, that the protocol uses, is the hydrogen to organic carbon ratio of the biochar. So that's required to be measured, and a number of work has been done at the small scale to show that this carbon to hydrogen ratio is a very accurate predictor of how of the stability. They think the biochar is stable because of this the fused aromatic structure of the biochar. And so this graph shows that as you the producing the biochar, you lose a fraction of the carbon, a good fraction. It's immediately released into the syngas, but then you've produced a biochar that's very stable. The 10% labile. Labile is the fraction of the carbon left in the biochar that's volatile, that will be lost. So if you've produced a really good biochar, that carbon will stay locked into that material over many, many hundreds of years. Alternatively, if you left it in the forest to decay, that would be that solid black line where you didn't lose the carbon immediately, but quickly over 5 years, you've lost most of it, and then over the following years, it continues to decay. So this shows that as the hydrogen to organic carbon ratio of the biochar decreases, the stability on the y-axis increases. So you get a more stable biochar, hundreds of years of mean residence time as the hydrogen to organic carbon ratio decreases. And I think we have one more of those plots again showing that as the hydrogen to organic carbon ratio decreases, the amount of carbon that remains after 100 years stays. The carbon stays in the biochar. So the protocol requires you make these carbon measurements, these hydrogen to organic carbon measurements. If the hydrogen to organic carbon ratio is less than 0.4, you can take 70% of, you can assume conservatively that 70% of that material will stay for 100 years. And then if the hydrogen to carbon ratio is not as good, is higher, you can only take credit for 50% of that carbon that you've stuck into the biochar. So this last slide just gives you a quick idea, and this is an estimate that if I have 1 bone-dry ton of biomass, I can produce on the order of 10% of that can be driven into the biochar. That biochar can be 70, it can be 50, the carbon content of that biochar can vary, but I've assumed here 75%, which might be slightly on the high side. But if you make those two assumptions, which are not totally unreasonable, we might project that you can get almost a third of a ton of CO2 benefit sequestered into the biochar per every 1 ton of biomass that you put through your machine. And I'm missing one slide. I apologize. The last slide was work that we're starting up again. We've contracted with Spatial Informatics Group, UC Berkeley, and the University of San Francisco to continue the work that Tadashi Moody discussed a couple weeks back on wildfire forest fuels treatments and the benefit or impact that those can have on wildfire emissions. And that work is being funded by both private and public partners at Sierra Pacific Industries, Forest Service, CAL FIRE, SMUD, Sacramento Metropolitan Utility District, and our district have put in some money to progress the work to hopefully in the coming years develop a very standardized procedure that can be used for valuing the greenhouse gas benefits of forest fuels treatments in terms of that impact on mitigating the size and severity of wildfire. So that was all I had today.
Thanks for the talk. Sorry for the presentation. It worked for me. I don't know why it didn't work for you, but maybe
Yeah,
we
I think
always have at least one gremlin.
I think we got most. We had everything essentially. So
Okay. Well, I wanted to mention one thing that I think might be important to some of the people that are at this webinar, and that's your emission factors that you have in the spreadsheet.
yes.
I think I have the link for the spreadsheet. I think the spreadsheet link will be posted on our website. People could use those emission factors if they are doing a treatment where they are doing pile burning or chipping to estimate their emissions for the greenhouse gas calculations.
Yes.
So that's very useful information for people that are going to have to do their application greenhouse gas analysis.
Yes, Richard. This could be both for the a proposal, an estimate, as well as an actual project that's run. Exactly.
Right.
Yeah. Yeah.
We've got a whole bunch of questions here.
Oh, okay.
Let's see. I think that the ones that pertain to you start with Mark. You outlined a number of reduced pollutants, but not CO2. Did he miss that?
Oh no. Yeah. Could I go back to the slides? Okay.
Yes.
So I may have spoke too quickly, or it didn't follow that. So this was the, and I'm not seeing the full graph. Are you guys not, Richard? Are you not seeing the full graph here as well? This graph was the CO2 benefit, the carbon dioxide equivalent of the biomass project. So the right side was the project, the biomass energy project. The left side was the baseline, and the difference is the greenhouse gas benefits. And to quickly explain again, the right side is that dark green is the CO2 released from the energy facility. The small bars stacked on top of it are the diesel fuel from the chipping and grinding and transport. And then the left side is the pile burn, the light green, olive green is the pile burn CO2, the dark orange is the pile burn methane, and then the dark purple blue is the avoided natural gas combined cycle to produce an equivalent amount of electricity that was produced in the biomass project.
Okay, right. I think.
Okay. And then
Mark is saying he just missed it. Yeah.
Okay. And then the next slide went through all the other traditional air pollutants that benefit from a pile compared to a pile burn.
Oh, and let me say that even though these graphics aren't showing up for us, the PDF of this, which will have the stable graphics, will be posted on the website, so you guys can take a look at that, and you can see these more clearly.
Okay.
Let's see what else we have here. Okay, are pile burns allowed all over the state?
Pile burning is done all through the state, correct? Air districts have open burn programs that are very closely managed that reduce the impacts of the smoke, so we only allow burning on certain days or at certain times that have been judged to be not cause issue, nuisance to nearby communities. But pile burning is allowed all through the state. Yes. There are, again, certain restrictions and requirements that you work with your local air district with. So.
John's asking, and I think this is the case, if black carbon is an issue with pile burning, it's also an issue with wildfire.
Correct, correct. I think some of the recent work is showing that, surprisingly, the pile burn will, as it burns more hot, as the temperatures get hotter, actually the black carbon content will actually be a little bit higher. Anyway, there's some trade-offs between whether pile burns produce more black carbon than wildfires, and per amount of material that burns, I think it will show they will. But wildfires do produce black carbon, absolutely.
Wilson's asking if the biochar protocol takes into account The biochar's benefits in a drought environment.
No, it does not. It does
No.
not. Unfortunately, right now, all it credits is the carbon that was stored or sequestered into the biochar that goes into the ag field. It does not take credit for all the other benefits that we think are there in terms of reduced water, reduced fertilizers, reduced improved crop growth. So none of those are currently factored in. There's some research to develop those better.
Jen's asking if there's a correlation between fuel type and resultant biochar. Does forest residue versus
Yes.
waste? Yeah.
Yes, there will be in terms of nutrients and potassiums and qualities of biochar. There absolutely will be. However, our protocol ignores those because we're focused. Unfortunately, we're just limited right now to the stability and the amount of carbon that was driven into that biochar, which we do feel is very conservatively estimated, again, through that hydrogen to organic carbon ratio.
David's asking if there's a benefit if a pile is left to decay in the field rather than burned. Just a matter of time, right?
Yes, there is a benefit, and that benefit is criteria. Our traditional air pollutants, will be there will be no fine particulate soot, CO, or NOx. So there's a traditional air pollutant benefit. The greenhouse gas benefit is unclear because the amount of methane that's produced from in-field decay and the amount of CO2 and that timeline is an uncertainty, is not really well established, and it depends on a lot of factors. We have some estimates in the protocol, but however, so there could be a greenhouse gas benefit, at least in the immediate term, for not pile burning it. However, our experience is that in the Sierra Nevadas, for fuel hazard reduction, pile burning is a critical. That's what's done because of fuel hazard reduction reasons. You don't take all the material, put it on the forest floor, and that would probably be opposite to the forest for the wildfire reasons you're doing it for wildfire control.
Okay,
I didn't describe that well. I'm not a forester, but
no, that's okay. Well, there's one other. You also have the issue of mastication, which results in a lot of material being spread in place.
yes, yes.
And I think Mark's asking about the timing benefit from the sort of decay in the forest option, and there obviously would be a timing question, because it's going to take longer for that chip or that masticated material. It's not going to immediately emit, but it will eventually emit.
Absolutely, yes. That's an excellent point, and our protocol was intended for pile burning because that's the standard procedure that happens in Placer County, foothills and mountains. But we did extend it to in-field disposal, either through chipping or just laying onto the ground. But there is some unknowns on that. Absolutely.
Okay, we better move on, Bruce.